All right, subscribers, welcome back to another episode of Science with Surback. Today what we're going to be talking about is sections 19.3 and 19.4 for the AP Chemistry course. Now, what this deals with is a more detailed explanation on entropy. Before we get going into the details of these notes, there are a few objectives that I want you to be able to meet by the end of this video. So objective number one is to be able to describe how entropy is related to the total number of microstates in a thermodynamic system. Describe how the number of microstates is related to the ideas of randomness of positions of particles and dispersion of kinetic energy. Objective number three, predict whether the entropy change in a given process is positive, negative, or near zero. Objective number four, state the third law of thermodynamics. Objective number five, describe how the entropy of a substance changes with increasing temperature and during a phase change. And objective number six, calculate the change or the standard change of enthalpy for any reaction tabulated from the absolute entropy values or that standard entropy value. Okay, so let's get started here. We have a lot going on and we'll get going with this. So we start out with this picture here and we have this gas expansion. Okay, and so what that tells us, or what this is showing, is a couple of things. One, we have all gases, or the entire gas, contained in this left side container, and you can see how the stop clock is closed. Now, once we turn that stop clock on, there are four possible arrangements that those molecules can occupy. So we went from one possible arrangement to these four possibilities. So those four possibilities here of the values are as follows. One, they can both be in the right. And that's the right container. Or vessel, if you want to talk about that way. Two, both could be in the left container. Three, one could be in the left, one could be in the right. And then our other possibility here is this, the other. So we're going to flip-flop sides here. It's hard to see in the black and white photo, but I'll say the other in quotation marks. Other in left container, and other in right container. Okay, so basically 3 and 4, they just switch positions. And again, these are different molecules here or a different number. Okay, and so we have these options here with our example. And I took some time here to explain this because we are going to use this. And I should say here, this should have the added word container. Okay, now again, those are possibilities here. And now what I want to talk to you about is, okay, well, what does that mean for us? We are only dealing with two molecules. And so what we have here is this. We need to talk about some probability. We need to bring in some stats. So we bring in some stats, the same exact picture that we just talked about, and we need to associate this probability. And so I'm going to put down here in this bottom right that if we have one molecule, so let's say we just have one molecule in this container and we open up the stopcock, the probability of finding both the probability of finding one molecule in one side of the container is 1 out of 2. Now, it's 1 out of 2 because we have two sides of the container here. Okay, so this 2 stands for two sides of the container. We've been calling them right and left-hand sides of the container. So in our example here, let's say we only want to see what is the probability associated with just finding all molecules here in one side of the container. So I'll pause and write that down. So again, this is kind of small, but it says, hey, what we're doing here is finding the probability that all molecules will be found in one side. Okay, so what we do here is this. We have 1 out of 2 to represent our two sides of the container. And now we only had one molecule of gas, and in this example now we have two molecules. So to be able to find, hey, what is now our probability, what we do, we take 1 out of 2 to represent both sides of the container and raise it to the n power. Now this n power right here, this is the number of molecules. Okay, so we now have two molecules. 1 out of 2 chances it can be in the side or one side. And so we raise it to the second power. And so what this means is that we have 1 out of 4 chances, or a probability of 25%, to find both molecules in one side. All right, so now if we have 3 molecules of gas inside the container, again, the probability of finding those 3 molecules all in one side would be half raised to the third power, which would get us 1/8. Again, our numbers of finding are all 3 of those molecules on one side. Now let's make it realistic here. Let's have a mole of gas, which is not unheard of. We can say half raised to a mole of gas, which is 6.02 times 10 to the 23rd. This right here, if you put it in your calculator, it would actually say 0, but it would be 1 over a big number. And this is really close to 0. So again, that 1 over big numbers is basically close to 0. So what this is saying is that there is almost or essentially 0 likelihood of finding 1 mole of gas in one side of the container. Now, this probability here is really associated with entropy, and so how we tie all this probability together is this. We have this scientist by the name of Mr. Boltzmann here, and he was able to say, okay, in reality, what are the chances of something like this happening? Well, it's very small. Well, I'm going to tell you why it's very small. And so what Boltzmann did is he did a bunch of stats work that was really similar to what we just did, or that was his basic premise. And he was saying here that he had he used the statistic probability to link the microscopic and the macroscopic worlds together. He did this via what he knew about entropy. And we'll get to that in a second in his formula that he used. What he did here is he used these items called a microstate. Now, a microstate is defined as a snapshot of the positions and speeds of all molecules in a sample of particular macroscopic state at a given point. So think of like an old school motion picture where each of those still shots, if you put them all together and you move that film, makes a movie or makes a whole show. He looked at each individual snapshot of a particular molecule or an atom, and he was able to tie together that entropy. A pretty ingenious thing used with stats. Again, these microstates are these very small pictures of how an atom or molecule or a compound is at one particular time. You tie all of those microstates together and you're able to get an explanation or a whole picture of what is happening. Now, I want to go a little bit more into detail here with the state of system and microstate. So I'll start out with the state of system. This is the macroscopic view of our system at a particular pressure. And on the flip side, the microstate is the particular microscopic arrangement that corresponds to a given state of the system. All right, so again, how this all ties together, what we just talked about, was we took those microstates, and that was a statistical view that Mr. Boltzmann had, and he was able to tie that into entropy. All of that relates back to statistics, and he was able to come up with an equation to explain entropy and these microstates and how they interrelated or correlated together. So what he did here, we're not going to go into too much detail, but what he did here was he came up with this formula where S for the entropy is equal to K, his constant, times the natural log of W for the microstates. Now you may look at this picture and say, hey, that's a log, not a natural log. Well, back when he was going through this process, there was no natural log versus log. It just was that logarithm. So that's how you get to that here. Now, what happens here of this is if we increase the volume, we're going to have greater number of positions available. So think of this as if we have more positions available, we increase the microstates. So think of this as more snapshots. Well, if you have more items or more snapshots in your motion picture, you're going to have a longer film. In this case, you're going to have a larger entropy. Okay, so more snapshots correlates to more entropy. Now, if we do a adjustment of temperature, so we increase the temperature here, again, now all of a sudden these particles get excited, right? They're gases, they're heating up, they're moving faster. The faster they move, the more microstates you have. And again, we can say, hey, more microstates means more snapshots, means more entropy. Okay? So it all ties together here of what we can do with Mr. Boltzmann's equation in this process here. A lot's going on here. Like I said, he used some advanced statistical methods. He used his knowledge of what he knew about entropy and what he knew about each individual snapshot or microstate and how that could affect the particular state of matter or compound or molecule that we are dealing with. Now, specifically, how Boltzmann got to these microstates is he looked at 3 types of motions and he correlated that to energy. So let's take a look at that. Okay, so each and every molecule, compound, any state of matter, any matter for that fact, has these three types of motion. You have translational, vibrational, and rotational. And so translational is just a atom moving from one point to another. Think of it kind of bouncing around a screen or bouncing around a container. Vibrational. These you can think of like solids, but every molecule or compound is going to have a vibrational motion. Think there's going to be some shaking or moving in that particular molecule. Now rotation, if we have a molecule, again, think of it like flipping or spinning in the particular container. Now we have some very important things that we need to think about here. Each of these motions require energy. And so if we have more motion, we have more energy, which means we have more entropy. So I'm going to tie a whole statement. This is for every single one of these. If we have more motion, that means we have more energy, which means we have more entropy. Some big statements here. And now we have some general statements that are just good to identify and read. So it says the number of microstates possible for a system increases with increases of volume, temperature, or number of molecules. Each of these changes, increase in volume, temperature, and number of molecules, increases the possible positions of kinetic energies and molecules of the systems. What that means for us is more entropy. Okay? Now, entropy, if we increase it, we're increasing the randomness or how dispersed something is, some particle is. So we have a lot going on. I know this is a lot thrown at you here new, but stay with the fact that, hey, as we increase temperature or volume, we're increasing microstates, which ultimately leads to this more entropy, and that's something that we are interested in here. And the other thing I do want to point out here with our last point is that this can also occur with an increase of temperature or volume. So I'll pause and write that down. All right, so let's apply this business here and go one step further, and let's do some examples to help solidify what we have going on here. Okay, so we have that statement that I just wrote down in pencil, and what I want to add to this is if we have an increase of temp or volume, we're going to have more freedom, or we're going to have more particles, and more free moving particles means more entropy. So let me pause and write that down. I'll add it to here, and we will go through some examples to go through this process. All right, so an increase in temp, volume, or number of particles means an increase in free moving particles equals more degrees of freedom. And so degrees of freedom is tied directly back to that energy or that motion, where we can talk about translational, vibrational, and rotational energy. More degrees of freedom means more entropy. Okay, so let's go through some examples. Melting of ice. You go from a very solid structure form to now you have these free-flowing particles. Again, what this results in is more free-moving particles. If we have more free-moving particles, just like we do, or just like this statement said here, we are going to have an increase in entropy. Okay, so this equals some more entropy. Now, let's say NaCl crystals dissolve in water. Now, this is a little bit more complicated than what it just looks like here. So I'm going to take this and we're going to do this example here. Now, typically when NaCl as a solid goes into water, it forms our sodium. I'm going to leave some space here. It forms our sodium, which is aqueous, and our chloride ions. Now, what is also happening here is this. We are getting the hydration, the water surrounding our Na plus and Cl minus. That's a result, or that's why the Na splits away from the Cl. So there you'd get the water to surround those particular ions, okay? And so what we can do, we actually have two different statements here, and that is that the Na and Cl cause more particles. So we have more particles, but what happens here is that the water, because it is now surrounding the Cl and Na ions respectively here, they also have a more order. So what's going to happen here is that as a result, this whole process here of what's happening being NaCl dissolved in water is we have both a ordering and a disordering process. Now, you may think, okay, well, what do we choose if we have both a disordering and ordering process? Well, usually the disordering dominates, and so that means we have more entropy. So I'm going to put ... Usually more disordering occurs, which means we have more entropy. Okay. Now, we get down to this equation here where we have 2NO gas plus O2, which is also a gas, goes to 2NO2. Well, check this out. On the reactants, we have 3 moles of gas. So I'm going to put this here. 3 mole of reactants. Okay? That are gases. All right? If you want to add that in there, that's perfectly fine. On this side, we only have 2 moles of gases. So 2 mole of products. So we have decreased the number of particles. As a result here, we've decreased number of particles, which means we're going to have less entropy. And then we get down to these guidelines here, and we have this. So it says normally entropy of a system will increase. So we might want to highlight these. Entropy increases when gases are formed from solids or liquids, when liquids or solutions are formed from solids, or the number of gas molecules are going to increase. So let's take that into consideration. I know there's a lot here, and I jammed a lot of information on this. Let's take that information and let's go and let's apply it to some additional examples. All right, so before we do these problems, I wanna make a little cheat sheet down here, and I wanna say, hey, we have delta S that is positive, which means we have an increase. We have an increase of entropy. Okay, so when there is a delta S that is positive, or an increase of entropy, this is going to occur when a solid is transformed or goes through the phase change to become a liquid. Again, delta S is positive. When a liquid is phase change or goes through a phase change to become a gas, delta S is positive. when a solid goes straight to being a gas, our delta S is a positive. And then if we have less, I'm going to say this, less particles to more particles, your delta S is positive. Now, let's go on the flip side here. And make our cheat sheet for when delta S would be negative, okay? And so, again, decrease of entropy would be our delta S being negative. All right, so if we go from a liquid to a solid, we go through that phase change here, delta S is negative. Or if we go from a gas to a liquid, again, delta S is negative. And also, if we go from a gas straight to a solid, your delta S is going to be negative. And then one more thing here. If we go from more particles to less particles, your delta S is also negative. Okay, so that's kind of our cheat sheet here to determine if our delta S increases or decreases and what a result is. All right, so our first example, we go from a liquid to a gas. Check this out, cheat sheet, liquid to a gas, delta S is positive, okay? So delta S is a positive, and I'm going to add a little bit to this. That means we increased entropy. Okay, now we go from aqueous, which you can think of aqueous as a liquid, not 100% correct. And then it goes to solid silver chloride. We also go from two particles on the left to one particle on the right. So again, more particles to less is negative. Also, if we want to think of it, liquid to solid is negative. Again, you don't necessarily want to say aqueous is liquid, but these are dissolved in water, which would have a similar function. So again, this is decrease in entropy. Now, we have on this, we have some different states of matter. So our states of matter aren't necessarily going to help us out. But check this out. Our reactants, we have 4 plus 3. So the reactants, there are 7 moles. 7 moles. And then on our products, we only have 2 moles out in front, or a coefficient of 2. So again, more particles to less, delta S is negative. That means we have a decrease in entropy. Now, our last part here, these are all gases, so the state of matter is out. Now we ask ourselves, reactants, we have 1 plus 1, so we have 2 moles. So reactants are 2 moles, okay? And our products are 2 moles, all right? Now we've kind of ran into an issue that we have to, or excuse me, that should be our products. Now we've ran into an issue that we have to deal with here. So here in this case here, we have gases. So we can't use the states of matter. The number of moles are equal. Here's what happens. Our delta S is equal to 0 because here what we have is it's impossible to predict those changes. Equal moles, equal number of states of matter, and we get to this process here. And if we want to write something down here, this is because entropy change is so small. All right, so we've added a lot of this. We kind of have that cheat sheet that we can use throughout this process. Now what we can do here is go to some more examples and talk or compare about which thing has more entropy when we compare two things. So keep that cheat sheet handy, keep that in mind as we go through this process here. So we have 1 mole of a solid sodium chloride versus gaseous hydrogen chloride gas. Okay, now the state of matter with the greatest entropy is that of the gas. So I'm going to circle this as the gas, and this is greater entropy, and that is because you're in your gaseous state. Now we go down to here. Both of these things are gases. However, the thing with the most particles, which is 2 moles of HCl, is our one with greater entropy, because there are more particles. Now we get down to this one. This one's kind of tricky because both of them are gases, so we can't rule out states of matter. Both of them are 1 mole, and so now we get to this item here. Now I'm going to draw this as our structure. So we would have HCl if we drew what we call Lewis structure, HCl, as this, and argon, which would look like this. Now, argon does not have as many degrees of freedom, and as a result is going to have less entropy. Now, if you want to know the specifics on that, argon does not have the vibrational motion. Because the definition here of vibrational motion is the shortening and lengthening of bonds, and this includes bond angles. Well, there are no bonds in the noble gas argon. It is by itself. It's that reason it's a noble gas, and so it's going to lack that vibrational motion. HCl is going to have more motion compared to that of argon, and so as a result it's going to have the greater entropy. Again, these are all good things to review, to understand, and to help identify what has more entropy and what could increase or decrease entropy. Again, just by looking at states of matter or number of particles, we can identify, hey, something's going to have more or less entropy, or we can have the comparison of what item would have more entropy. All right, so let's get into this. We get into one of our final topics here for section 19.3, and that is the third law of thermodynamics. And it says the entropy of a perfect pure crystal at 0 Kelvin is 0. So at 0 Kelvin, you would only have one microstate. Now you can see there is no translational, rotational, or vibrational movement, and so if you have one microstate. If we use Boltzmann's formula that says K times the natural log of W, and we plug some values in. I don't even need Boltzmann's constant. I'll just say K times the natural log of our microstate, which is 1. If we take the natural log, and you can do this in your calculator, if you take your natural log of 1 and we throw it in there, natural log of 1, we get 0. What this means is that this means S equals 0. All right? And so what we have to think about, if we started at 0 Kelvin and we increase the temperature of that perfect crystal, we're going to increase entropy. Okay? So again, we kind of tie together our second law of thermodynamics, which says for a spontaneous process, we can get more entropy in the universe, or the entropy of the universe increases. Now, we say here that molecules gain that vibrational motion, and they also have more degrees of freedom, which we've already talked about how that can increase your entropy. Now, I want to add 2 things to the end of our third bullet here, and that is this. When a solid melts, the molecules and atoms have a large increase in freedom of movement. The other point that I want to make here is that boiling is going to correspond to a much greater change in entropy than melting. And this should make sense because as something is boiled, you have particles go to the gaseous phase. And so something that's going to the gaseous phase is going to have more degrees of freedom, which we've already said more degrees of freedom means that we can have more microstates or an increase in entropy. All right, so we got real deep, we got real theoretical here. Let's kind of put this in perspective here and do some calculations with this process here. Okay, so we can use the third law and we can help find some delta S values that can be shown. Now, we can't just calculate delta S like delta H. These things have to be measured experimentally, and the experiment process is kind of difficult to explain, and it's really a tedious process. Now, what I want to point out is 2 things here, okay? Notice that when a substance melts, there is no temperature change. So no temp change when a substance melts. But we have an increase of entropy. And the reason for this here is that when a substance melts, there's more degrees of freedom, okay? So I'm going to call this more DOF for degrees of freedom. And maybe I ought to note that here. DOF is degrees of freedom, okay? Now, I'm going to say this again for our boiling. When a substance boils, there is no temp change, but there is an increase of entropy. Again, same reasons, more degrees of freedom. So I'll pause and write that down. Okay, so we've talked a lot about delta S, and it says, hey, no method to calculate delta S like delta H, but let's get into something that we can actually use and go forward and go through this. So that brings us to our standard molar entropy, okay? So our standard molar entropy is defined as the molar entropy of a substance in its standard state. Remember, we should already memorize this, but standard state is 1 atmosphere of pressure and 25 degrees Celsius. Now, what happens here is this. We get a very similar looking format that we use for delta H, and I'll bring out the periodic table packet to help us out with that. But remember this, The only time we're at an entropy of 0 is when we have something at 0 Kelvin in its pure crystal lattice format. So something's always going to have a S or a entropy in standard state, because 25 degrees Celsius is obviously nowhere near 0 Kelvin. So we have to keep that in mind here. And with this, the entropy of a gas is going to be a lot more, because we have a lot more degrees of freedom with a gas compared to that of a liquid or solids. Now, with delta S, or with our standard entropy here, it's going to increase with a bigger molar mass and number of atoms in the formula. And these are just general trends that we go over. Now, I want to look at a couple of things in our formula. Obviously, our delta S is the change of standard entropy, but your N, just to remind you, your N here is number of moles in that chemical formula. Your S is your standard entropy, which can be found in our appendix C. If we look under here, look, we have the standard entropy, S with the little degree sign here, and it's listed for our compounds, very similar to delta H. So I'm going to say found in appendix C. And then you have products minus reactants, okay? So we have to keep that in mind as well, okay? And then your epsilon here, that just means add it together. Your Greek symbol here means the sum, okay? So let's go ahead, let's utilize this appendix C, and let's go through an equation. All right, so here is our equation. It says calculate the change in standard entropy of the system, delta S, and standard conditions for the synthesis of ammonia from nitrogen and hydrogen at 298 K. Remember, 298 K is equivalent to 25 degrees Celsius, and we're under those standard conditions. Now, I want to point out a couple of things. I'm going to write the formula down just so we have an idea, and that is delta S, the little degree sign, is equal to the sum of our delta, our S values times your products. Make sure we put products minus reactants, minus the sum, number of moles, S of your reactants. And so what I like to do first, before I like to start plugging numbers in, is I like to list out my products and list out my reactants. And while I do that, I want to be able to identify that standard molar entropy found in our table. So lucky for us, we only have one product, which is NH3 as a gas. Remember, states of matter because we're going to find some of these substances in different states, and we need to know which one we need to write down. So again, appendix C is located or shown in numerical atom order, and so we get to nitrogen here, and we start looking, if I can find it. We start finding nitrogen, NH3, as a gas. We want that gas form, and we want the delta S. So we're going to scroll all the way over. That is 192.5 joule per mole Kelvin. So again, we just looked that up in the chart. And I'll say this. Remember, there is no negative entropy in these tables, okay? So we should not have that. Now, we're going to go over here to our reactants. And we do have two reactants that we need to worry about here. And so if we have this, our N2 as a gas, We look this up, nitrogen as a gas, N2 as a gas. We scroll over, has a standard entropy, this last value, 191.50. 191.50. And again, if you looked at that chart, that is in joule per mole Kelvin. Okay? Now, hydrogen, H2, is also a gas. And if we look up hydrogen, on our chart, we find H2 as a gas. We scroll all the way over to the last column. We find it 130.58. And again, this right here is joule per mole Kelvin. Okay? Now, we need to plug this into our formula here. And we're going to take some space here. So delta S, we start out here with this. We start out with our products. Our products, we only have one product, and that is NH3. The number of moles is equivalent to our 2 out in front, so we get 2 moles of NH3. And we multiply it by the S value we looked up. So we multiply it by 192.5 joule per mole K. Now, that's our only product, so we can go ahead, close the parenthesis and close that bracket. And then we're going to subtract it, and I'm going to write it down just because I'll run out of space. Subtract it from our reactants. So we start out here, number of moles of nitrogen. Well, we have 1 mole of N2. 1 mole of N2 times our value here, which we looked up. Our S value is 191.50 joules per mole K. We add that to another set of parentheses, number of moles of H2, 3 moles H2, times 130.58 joule per mole K. Okay? Now, very important that we plug this into the calculator correctly. All right? So, what we have here is this. We have our 2 sets of parentheses. 2 times 192.5. We close that set of parentheses. We subtract it from double set of parentheses. 1 times 191.50 plus 3 times 130.58. We close that set of parentheses. And we get a value of negative 26.24. And I was just double checking my calculation. I might have put in an error here, but again, I enter all of this again. And what we should get here is negative 198.24 joules per Kelvin. And again, that is a negative value, joule per Kelvin. Okay? Now, we can go a little bit further, and we can go a little bit further here, and we want to figure out, okay, for an isolated or an isothermal process, delta S is going to be calculated using this provided formula. Okay? So delta S of the surroundings is calculated using this formula. Now, I wanna put some things into perspective here, and that is this. I'm gonna write it below, and that is delta S of the universe is equal to delta S of the surroundings plus delta S of the system. Well, what we just found on the previous page, was the delta S of the particular system. Okay, so this right here, delta S of the what we just tabulated is delta S of the system, and so I'm going to put that up top here, and so delta S of our system is going to be negative 198.24 24 joule per Kelvin. Okay, so keep that in mind there. And what we have going on here is this. We can substitute this out for, instead of having Q of the system, we can say delta H of the system. Okay, so we can say this is equivalent to the delta S of the surroundings is equal to the negative delta H of the system over T. Now what we can also say is that we can calculate the delta H of the system. Okay, so what we can do here is we can calculate it, can calculate this value via delta H of the reaction. Okay, so delta H of our reaction. Now, a little extension here, our delta H of our reaction is, remember, equal to the epsilon, number of moles, times your standard enthalpy there, or your change in enthalpy. Your delta H times your products minus the sum of the number of moles times the delta H of your reactants. Now, these values, these are delta H values, and so where we would get this is from our chart, but now we have to deal with delta H, okay? So here we go on this one, all right? So our products, or I guess our product in this case for this same reaction, is NH3. NH3. What happens here? NH3, we look at that first, it's a gas. We look at that first chart, negative 46.19. So we get negative 46.19. And then we can do the same thing for our reactants. And so what we do here, and this was kilojoules per mole, our reactants, okay? Our reactants are N2 and H2. Okay, so N2, the delta H value looked up on this chart for a gas, our N2 for gas is 0 kilojoules per mole. And I should note this was a gas as well as nitrogen was a gas. We do the same thing for hydrogen. As a gas, we get hydrogen as a gas, H2. Hey, this is working nice. 0 kilojoules per mole. So 0 kilojoules per mole. Okay? And so what happens here? What happens here is this. The delta H, the standard delta H of the reaction, is equal to, bracket, our number of moles of NH3, 2 moles NH3, times negative 49.19 kilojoules per mole. You close the bracket, you subtract it from 1 mole, N2. 1 mole N2 times 0 kilojoules per mole. It's going to be nice there, kilojoules per mole. Close the parenthesis, you add that to 3 moles of our H2. And again, H2, we just looked up the delta H value of 0 kilojoules per mole. Hey, if you haven't noticed, it's 1 times 0 plus 3 times 0. This whole thing's going to be 0. Now I'll punch it into the calculator just to show you that. But we're going to get 2 times negative 49.19, close the parentheses, minus 1 times 0 plus 3 times 0 And we get a value of negative 98.38 kilojoules per, or just kilojoules. So the delta H of the reaction is equal to negative 98.38 kilojoules, okay? Now, what we do is this. We still need to find the delta S of the surroundings, okay? So the delta S of the surroundings is negative the value we got here. So negative 98.38 kilojoules per the temperature. Remember, this was under standard conditions. So it says, hey, standard conditions, we are at 298.15 Kelvin. So this is at 298.15 Kelvin, okay? And so what we can do here is take negative makes a positive 98.38 divided by 298.15. We press enter. We get a value here of 0.32, by the time it rounds, 0.330. So 0.330 kilojoules per Kelvin. Now, this right here, if we multiply it by 1,000, is equivalent to 330 kilojoules per Kelvin. So I'm going to write that down. 330 kilojoules per Kelvin. Joules per Kelvin. And the reason I did that is because we calculated the delta S of the system to be in joules per Kelvin. So now, to find the delta S of the universe, we have this. We take our surroundings, 330 joule per Kelvin, and we add it to negative 198.24 joule per Kelvin. Again, same unit, that works out nicely. So I'm going to take 330 plus negative 198.24, and our delta S of the universe is 131.76 in this particular process. So the delta S of the universe equals 131.76 joule per Kelvin. Hey, let's talk about this just briefly. Delta S is positive, okay? So delta S of the universe is positive. This means entropy of the universe increased for this process. What that means is, hey, we abided by that second law, second law of thermodynamics, where it says, hey, the entropy of the universe is going to increase for a naturally occurring process or for a spontaneous process. All right, so we did a lot of math. There's a lot going on here. Biggest thing you can remember is, hey, am I asking for delta S? Make sure you use the right values. Delta H here can also be or needs to have the right values, and we can tie all of this back to our formula we've seen before, where delta S of the universe equals delta S of the surroundings plus delta S of the system. Learned a lot. Hope you've enjoyed this episode, and if you haven't already, make sure you subscribe.